and he is going to cover effective microorganisms and economical and ecological alternative for soil biological renewal. That's a lot of big words. Can't be chewing gum and say that at the same time. All right, so for our agenda today, we're going to go over a little meeting ground rules. Our last meeting, we had a little trouble with a couple of bombers that hit our meeting. If that happens during our meeting, what we'll do is we'll all log out, and then our administrators will take care of that and give it about 2 minutes and log back in, and then we'll just continue with the meeting. Of course, meeting etiquette as we go through. Everybody please try to stay muted during the meeting. What we're going to follow the format of, we're going to let Mr. William talk for about 45 minutes or so. Then we're going to do a little 5-minute intermission where we're going to do our poll. And then after that, we're going to open it up for Q&A. And the way we're going to do our Q&A is you will ask the pro-organic host through the chat functionality your question, and then Jenny will restate that question to William, and he will give us his answer, and we'll go back and forth like that, and we'll control the questions through that method, so we won't have everybody trying to speak at one time. All right, and then on to everybody who doesn't know the pro-organic organization as of now. Hopefully you've been to our Facebook page where we post all of our pro-organic events. So if you want to find out about what's going on with pro-organic, you can go and like the Facebook page and see everything there, including these speaker meetings. We also record these speaker meetings and we try to post them onto the Facebook page. So if you miss part or all of this meeting, you can always go there and find it. Then we also have the pro-organic group on Facebook, which is like an open discussion where you can post questions or post things related to organic farming or agriculture or produce, ask questions, and then interact with people in the community. And about the organization itself, we have, of course, are a member organization, so we're always trying to get new members and members that will volunteer within the organization to help out in one of our committees or helping out in some of these events that Pro-Organic puts on a monthly basis. And then some of those committees, we have a marketing committee, which puts together events like this. We have a farm certification committee that goes out and certifies farmers as pesticide free. And then we also have a consumer group that helps get that pesticide produce out to the consumers. And moving on, continuing with our agenda. Hopefully everybody knows that we are here to talk today about the importance of microorganisms in our soil. This is going to be about a 45-minute long presentation. Hopefully everybody knows Mr. William Usher. After he does his 45 minutes presentation, we will go into about a 5-minute poll where we'll ask you some questions about how you found out about the meeting and so on. We need to collect a little information so we can better present these meetings to the public and everybody can find these meetings. After that, we're going to go into about a 30-minute Q&A. And like I said, you ask your questions to the chat functionality to the pro-organic host, and then Jenny will come on and she will ask William those questions and he will answer them. After that, we'll have a little conclusion session and then we will conclude our meeting. All right, so let's move on to Mr. Williams' presentation. Mr. Williams is going to tell us a little bit about himself, and then he has some slides that he wants to go over. The floor is yours, Mr. Williams. William, I think you're still on mute.
Okay.
Perfect.
Guys, I am hoping that my internet doesn't get too unstable here. For some reason, I'm in my office today and uh, I just noted a little sign there. So excuse me if we have a little problem. Well, to start with, introducing myself, I'm William Usher. I'm a agricultural engineer by profession, and my specialization is bioresource chemistry. I'm also the owner of and partner of Belize Agro Enterprise Limited, that is the licensed manufacturer of effective microorganisms. That is the original Dr. Higa microorganism technology. Uh, Today, as Rick said, I'm going to speak about microorganisms and, in a nutshell, how they work and relate that to the technology that we have in terms of soil. So, to get on with this, Rick, definitely I'd like to be able to share my presentation.
I think if you go down to the bottom of your screen, you should have an option to share.
Uh, all I am seeing is participants invite chat record.
Um, do this. Turn your. You see where you can turn your video off. You might have to turn your video off, and then it should be a bar at the bottom of your screen where you can share.
Switch to video. Okay, I am stop video. That's what I should do.
No, 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 don't stop.
Oops.
Right. Okay, yeah, and see if you have a icon down at the bottom of your screen that says share screen, and I think it should be green.
Oh. Basically, the presentation will be about effective microorganisms, an economic and ecological alternative for soil renewal. Uh, I won't be putting a whole lot of numbers in terms of economic issue. I'll just more speak about the areas of where you would possibly see savings. So to start off this whole presentation, I like to start my presentation from an agricultural standpoint in terms of challenges. And the reality is the challenge ahead for farmers is to produce more food on a declining land area with soils and ecosystems that are continually being degraded, all while using less water, energy, and natural resources under difficult economic circumstances. That's basically where we find ourselves as farmers today. And the question is whether we can solve those challenges to rebuild degraded soils, whether we can solve those challenges to increase soil fertility, to produce more nutrient dense food and forage, and using less water to grow crops and increase both plant water use efficiency and soil water storage capacity. Of course, another is whether we can reduce energy use by allowing nature to extract or fix essential nutrients, and whether we can reduce both agrochemical pollution and atmospheric carbon dioxide at the same time. Obviously, I ask all of these questions, and a lot of time people think that they are difficult or impossible, but the reality is microorganisms in the soil can allow for all of that to occur. No, so most importantly, of course, within this question is, in the end, can we improve productivity and profitability? And that's what will allow any farmer to decide whether they will do something, whether they will make a change towards a particular technology. There are three simple steps to build soil and make them more healthier and productive. And the guys who are into regeneration agriculture, which is all of you guys that are here on the platform, I imagine, or that you are interested in that, uh, one of the most important is to disturb the soil as little as possible. The less we disturb the soil, the more possibility for microbes naturally to access that soil. Maintain some sort of ground cover, be it in conventional agriculture, organic agriculture, regenerative agriculture. That is a key component in order for microbial survivability. And of course, having a diverse mix of plants and or animals where possible. Different systems, you might have animals, other system, it's just a diversification or diverse plants. Nonetheless, in monoculture agriculture, there is room as well to improve soil building capacity with microbes. The problem, however, even with all of these things, say if you are trying to transition from a conventional agriculture to organic to sustainable agriculture to regenerative agriculture, the problem is always establishment time, and there is an economic cost in that transition, whether it's in time costs, whether it's in the need for input to those production, there are costs there. And that tend to be one of the biggest problem for any kind of transition from conventional agriculture into any of these sustainable type agriculture. Nonetheless, we believe that there is a solution to that. And that solution basically is soil biological renovation. And that obviously can occur once you are inputting biologicals and inputting carbon source within the soil. And that's where I am going in terms of the presentation. Everyone hearing me? If you are, I will continue.
Yes, we can hear you.
Okay. The question here, microorganism and soil carbon. These are the two most important things when it comes to nutrient cycling. And we will discuss a bit why. It's important to understand that there is a direct correlation between plant growth and organic matter. Both in terms of plant growth, it is certainly higher in microbial inoculated soil. No? Organic matter, another important issue, is the energy resource for microbes in the soil. It's very important. And when I'm talking organic matter, compost gets converted into soil organic matter, gets converted into humus, humic acids, and other essential amino acids within the soil. These are what we are talking organic matter. They are the energy source for microbes in soils. They are essential for healthy soils, and they are essential in increasing soil productivity. A soil that has, or say, a low carbon system tend to reduces the photosynthetic energy captured by plant that would go into growth. And why is this? Because as you will see in the nutrient cycle that I will show, Plants are always capturing carbon from the air because they need it for photosynthesis to make their food. And that energy, that carbon, that energy that is created, they either use it for growing. However, if the microbes association that is necessary for that plant is not there, the plant will automatically allow for these nutrients, these carbons, these sugars to exude through its root so that the microbes could start being attracted to those association will come about. So low carbon system, the plant will allow for carbon to be created, to be transferred from the air to the bottom. And why we say that? No, plant grow better in microbial inoculated soil, as we say, and the fungal and bacterial ratio is higher in those microbial inoculated soil. And what does that mean? It basically means higher fungal ratio plus higher carbon content, increase energy flow into the plant, right? And that is what allows for plant to increase production. So those two things are very important. It doesn't matter which type of agriculture you are doing. You want to sustain that agriculture. You want to improve the fertility of the soil. Those are the two things that you have to concentrate on: increasing the carbon content, increasing the microbiological content. Two important concepts. People hear it all the time: carbon sequestration, nutrient cycling. I'll try to explain that as simple as possible, because the reality is it's very simple for you to understand. And when we are talking carbon sequestration, we are talking about this activity within the soil. How does it work? Basically, plant absorb carbon from the atmosphere during photosynthesis. They produce simple sugars and other related compounds, amino acids and other stuff, and they exudes that. About 40% of the carbon-rich compounds goes into the soil and speed up specific groups of microorganisms, bacteria, fungus. Under natural condition, this occur, right? But why do they do that? Because they expect to receive nutrients in return. The plant naturally do not receive all those nutrients from the atmosphere. The plant mouth, the feeding component of the plant, is the root. And so when I say why do they expect to receive nutrient in return, it's because from the soil, they produce all these carbon-rich compounds and they emit it within the soil, and it's the microorganisms within the soil that takes that and eventually uses that to allow for nutrients to come to that plant. And I will now show this quick little video here by Dr. Elaine's Soil Food Web School. Guys, if you go to this site, you will see a lot of things that could assist you to understand the whole issue of soil. Without all a lot of technical terminologies, etc. But it's really good. So I will go to that point, and after that, I'll come back to the presentation. Please let me know if you are hearing the presentation. I'll pull my mic and put it towards the video if you are not hearing. I'll go to full screen this time.
Nada, William.
Hello? Are you hearing?
Nada. I hear you, but there's no video.
Okay, just a minute. Are you hearing?
Now we are.
You're hearing now.
I hear
Yes.
you, but I see no video. I think
Oh.
you need to stop sharing and then switch
Okay.
over to sharing the video.
Yeah, William, what you'll have to do is stop sharing and start the video and then share again and select the video.
Okay, let me do that. Okay, let me start. Are you seeing the video? Are you seeing my screen right now?
Yes.
I'm still seeing the presentation.
Okay, just a minute. Are you seeing the video now? I switched.
Yes.
Yes.
Yeah, now we
Okay.
are.
Okay, I'll start again.
There's no audio.
Are you getting the audio now?
No,
You're getting no audio. Well,
correct.
okay. Let me. What I'll do, I'll just put my mic.
Have the video muted.
Yeah,
William,
on the-
you have the video
yeah.
muted on the
Yeah,
player.
unmuted.
Are you hearing it now?
No,
You're still not hearing it, right?
even unmuted, I'm not hearing it.
See
You're
if you-
still not hearing it, right?
see if
Right.
you can turn up the volume on the player.
Hang on. It's on the loudest I could possibly have it. You're still not hearing it.
Correct.
not
It's
hearing it.
good.
Okay. Let me do something.
Plants combine carbon
Yes,
dioxide
hearing it now.
and sunlight to
Okay.
produce simple sugars and carbohydrates. But just like humans, plants can't live on sugars and carbs alone. Fortunately for plants, there's a rich source of nutrients right under their feet in the soil parent material and in organic matter. When dead plant material, or organic matter, falls to the surface of the soil, it's gradually decomposed by microorganisms. Nutrients are then released into the soil in plant-available form. The next generation of plants then absorbs these nutrients, and so nutrient cycling begins again. We humans remove nutrients from this cycle when we take food from our fields, but these are easily replenished when microorganisms harvest nutrients from the parent material, the rocks and pebbles, and the much smaller particles such as sand, silts, and clays. At the molecular level, the parent material comprises large lattice structures which hold nitrogen, phosphorus, potassium, boron, calcium, iron, and all the other nutrients that a plant needs. With a balanced soil food web in place, plants can control the nutrient cycling that's happening in the root zone. They invest some of the sugars and carbs they produce during photosynthesis into the soil in order to feed bacteria and fungi. This causes bacterial and fungal populations to increase dramatically. The bacteria and fungi then get busy harvesting nutrients from the organic matter and parent material, absorbing these nutrients into their bodies. Predatory microorganisms are attracted, and they begin consuming the bacteria and fungi. The wastes left behind by these predators contains an abundance of nutrients in plant available form. These are easily absorbed into the plant roots. So the plant gets a good return on its investment, exchanging sugars and carbs in return for all the other nutrients it requires. This results in well-nourished, resilient plants and in nutrient-dense food for us humans. With a balanced soil food web in place, plants are able to access all the nutrients they need on demand, simply by varying the compounds they release into the soil. This means that farmers don't need to waste money buying and applying fertilizers. The soil food web costs very little to maintain by comparison. Having nutrient-rich plants results in greater yields and improved quality of the produce. Reduced costs and greater yields result in dramatically increasing profits for many farmers who have used the soil food web approach. The nitrogen-based fertilizers that farmers use are made using huge amounts of fossil fuels. Only around 40% of these inorganic fertilizers get absorbed by crops. The rest is either volatilized, polluting the atmosphere, or it runs off polluting our rivers, lakes, and oceans, causing algal blooms and dead zones that are a major environmental problem. So restoring the soil food web leads to nutrient-rich food for the consumer, increased profits for the farmer, and also benefits the environment. For more information about the numerous benefits of the soil food web and how you can get involved, please visit soilfoodweb.com.
Okay. Okay, guys. I'll come back. Me?
Yes.
Okay.
Yep.
I will come up now to, in a nutshell, basically what the nutrient cycling is all about is microorganism harvesting nutrients from soil organic matter and also from the parent material, which are the rocks, etc. Plants are not capable of directly accessing the nutrients in these structures as you saw there. And it's really the beneficial bacteria and fungi that produces enzymes that break down these structures and release nutrients. And in the end, those same microbes absorb these nutrients, and later on when they die or when other predator microorganisms eat them and releases their waste, that waste basically are what the plant absorb under natural conditions and the organic conditions. So there is where we are saying and showing why microbes are very important within the soil. Now, what are the important role of microbes in the soil? As you note there, the mineralization of organic matter, that's that's a key component. So that compost that you're putting down there, yes, you will have larger insects, larger organic organisms breaking that down, but in the end, it's the microbes that will mineralize that organic matter. Microbes fix nitrogen as well within the soil. They are responsible, they release organic substances that allows for root growth, such as gibberellic acid, indole acetic acid. All these are produced by microbes naturally within the soil. They produce enzymes, vitamins. They're responsible for soil aggregation and stability. If you saw within the little video, it spoke about how they release certain uh, metabolites that are sticky substances that brings different pebbles, etc., to form larger aggregates. You know? They produce phytohormones, hormones that are responsible for growth, for photosynthesis, etc. They also are responsible for the absorption and movement of minerals by the plant. Chelation of minerals, that is basically holding minerals and allowing for these minerals to go within the plant. Not necessarily the microbes doing that, but because they form these organic acids. These organic acids are what does the chelation, the mineral solubilization again. And importantly, where I'm coming at now, the EM technology has beneficial microbes that are doing all this when you are applying this technology within the soil. And that's where I'm going at this stage. EM technology and economic and ecologically corrective alternative. Um, and here I'm speaking EM1, which is a microbial inoculant, soil inoculant that are EM agriculture. And then you have the natural insecticide EM5. What is in EM technology? EM actually means effective microorganisms. The original EM was discovered by Dr. Terohiga, and the discovery is actually of the interaction of beneficial microorganisms. That's what he discovered, and within this technology, that's what is comprised within the 86 plus different microbial species that is within that technology that form a coexistence with each other and co-prosperity within each other for allowing for sustainability where the technology is used. So what is EM technology? It actually consists of certain groups of microorganisms that are well known within the natural environment. All the microbes within EM technology comes from within the natural environment, from within the soil or from below 200 meters under the sea. They include the families of Lactobacillus, Saccharomyces, and other microbes that are not noxious, not pathogenic, not genetically modified, nor chemically synthesized. In general, how they function is that they act specifically on organic matter. That's why using EM technology, one of the first in organic agriculture is not a problem. You see complete transformation in that area. And when we use it in terms of monoculture activity, we see better results where the soil organic matter is higher. And so part of our management where the soil organic matter is very low, we recommend adding humic acids and other organic component within that area. But it's a known fermenting process where EM is used. It accelerates decomposition, as you heard within the video what microbes do. And EM technology actually work in two principal ways. One, by competitive exclusion, where they are able to suppress pathogenic microorganisms. As you note, we within the video we speak as well of good microbes, bad microbes, and I will explain that a little bit more as we go forward. And the other is that these microbes produce beneficial substances such as vitamins, amino acids, antioxidants, and enzymes. So allow for growth and allow for an environment where beneficial microbes grow. For example, the lactic acid bacteria, they are strong stabilizers. They suppress harmful microorganisms naturally. They're also responsible for increasing rapidly the decomposition of organic matter. That's why using this technology, for example, to do compost, we can do composting in half the time that it will normally take without adding these microbes within. And for example, the yeast, they also have produce bioactive substances such as hormones and enzymes responsible for promoting root cellular division, root growth, etc., and fruit growth. And then there are other microbes as well that is responsible for creating an environment where beneficial microbes uh, that actually love oxygen start coming, and those are considered more the beneficial microbes.
Could I ask a question, William?
Yes.
Hold on. If you need to ask a question, use the chat functionality to put your question to the pro-organic host, and then Jenny will ask the question during the Q&A section.
Thank you, sir.
Okay.
Yeah. Basically, as you use effective microorganisms, as they decompose organic material, they does it under fermentation. So basically, they are antioxidative bacteria, and as they decompose organic matter, they are producing these amino acids. But importantly is that they produce water and they produce oxygen, uh, and not methane and nitrates, which is not really consumed by the plant. Ammonium is what more consumed by plants. Here I will explain how EM works, what it does in terms of the scheme of things. As we say, EM equilibrate the soil biological environment to allow for renovation. No, under neutral environment. When we say neutral environment, we are talking a primary forest, for example. You tend to have far more neutral or opportunistic microbes dominating that environment. All these microbes are there, whether they are pathogenic or non-pathogenic, they are all there. Just that environment is balanced, you know. And when you start creating that environment, mechanization, agrochemicals, whatever it is that you're putting within the soil, you eventually start creating an environment, maybe not by your choice, but simply because of the methodology that you are using. You eventually start creating an environment where these opportunistic microbes, the harmful microbes will always be the harmful microbes, but it's the opportunistic microbes, they start working in that oxidative environment because they have the ability of working on both sides of this seesaw scale that you see here. And so under that oxidative environment where you start having less oxygen, less aeration, you start having these problems where these harmful microbes such as Phytophthora start becoming dominant within that environment because you have these guys shifting over. Nonetheless, under the EM technology, say for a regenerative environment, what happens is because you are putting in beneficial microbes, nature would tend to normally do this, for example, in regenerative agriculture when it stabilizes. But before that happens, uh, by you putting in beneficial microbes, you actually start creating that environment where these opportunistic microbes will start moving towards that antioxidative area where they are producing amino acid. So you start having in time more of the beneficial microbes within the environment, and that's where they start doing the good things that you saw in terms of the nutrient cycle and how the role the microorganisms play. Here, there is another video, and I'm sure you'll probably hear this one because my mic isn't in the computer. But this is just what we'll show you here is soybean seed germination, where you're just using the beneficial microbes compared to another area where you are not using the beneficial microbes. just to show you that with EM alone, how these seeds will germinate. So let me start that and see if you will get that presentation.
William, it's working.
That video basically shows what happens when you're using beneficial microbes within a particular environment. You're just applying water there. Yes, the plant needs water. Yes, that will eventually occur. But once the beneficial microbes are dominating that system, everything speeds up. And that's basically what I wanted to show there. Uh, Using beneficial, there are other benefits. Now, all of these things that I'm talking about, when you start having increased rate of germination, those are savings, those are cost savings. When you start having inhibition of pests and diseases, those are cost savings because no longer you need pesticides or reduce the amount of pesticides you need. When you start able to suppress weeds, again, the same thing happen. You start reducing costs. So let me go to this one video here in terms of inhibiting pest disease. I think you'll be able to hear it again. If not, then I'll just have to go back again. But let me know. You should be able to hear it.
William, and that way it should open up in YouTube, so you have to quit sharing and then share the YouTube video.
Are you hearing?
So, how does the soil food web inhibit pests and diseases?
Yeah,
Well, if you've watched
we can hear, but we can't see the video.
Okay, let me move out.
they release oxygen and produce sugars, carbohydrates, and other long-chain molecules that are mostly made up of carbon atoms. Plants release up to 40% of these carbon-rich compounds into the soil as exudates to feed fungi and bacteria. They do so in order to promote growth in the population.
Okay, guys. Sorry there, guys. I sharing the wrong video.
Well, if you've watched the animation on building soil structure,
You're
then
seeing
you'll
it.
know that these anaerobic organisms in rich environments. That's because these anaerobic organisms don't do well in an oxygen-rich environment. This means that they are easily outcompeted by the beneficial aerobic microorganisms that do thrive in oxygen-rich environments. Access to foods for the anaerobic microorganisms is severely limited by the competition from the beneficial aerobic microorganisms, making life even more difficult. The sugars and carbs that are put out by the plant are released from the roots in order to feed beneficial microorganisms, as explained in the animation on nutrient cycling. Naturally, these beneficial organisms congregate around the roots. In fact, they totally cover the surfaces of the roots in order to get immediate access to this valuable food source, thus making it very difficult for anaerobic organisms to access the food supplied by plants. As the surface of the roots are covered by beneficial organisms, the microscopic infection sites which the disease-causing organisms are looking for cannot be accessed. So the plant roots are very well protected against infection. But what about the above-ground part of the plant? Well, it just so happens that plants release sugars and carbs from their leaves too, and from their stems and fruit. In fact, from all parts of the living plant. And the beneficial microorganisms can be found there too, feeding on the compounds being released by the plant and providing protection to the infection sites in return. Here's an interesting thought. Imagine picking an apple from a tree, and the surface of that apple being completely covered in beneficial microorganisms. What effect do you think nature's little defense force might have on your gut biome? So, without access to food and facing oxygen-rich soil conditions, the bad guys are severely weakened. Many of them are consumed by aerobic predators. Insect pests can also be a problem for farmers. These are much larger than the disease-causing microorganisms we just looked at. But real-world trials trials have shown that with a balanced soil food web in place, insect pests are deterred from attacking the healthy plants that are grown. Healthy plants produce chemicals that deter pests, whilst plants that are stressed are less able to do this, and so they're more susceptible to attack. Having the soil food web in place results in cost savings for farmers, as they no longer need to spend time and money spraying pesticides. And they also see their yields increase, as less plants are attacked. According to the UN, pesticides are largely to blame for the decimation of insect populations by approximately 25% per decade over the last 30 years. Bird populations are also crashing as a consequence. There is mounting evidence that the human biome is one of the most important factors in human health. Could eating food grown in natural soils be good for our health? We at the Soil Food Web School think so. For more information about the numerous benefits of the soil food web and how you can get involved, visit soilfoodweb.com.
So in terms of weed suppression, and there are several others, you guys could go on that website and see the other videos there to understand simply how it works. But what is important here is that farmers have to understand that 90 to 95% of the disease, pest and disease, that you find on that plant, whether in the root or on top, above ground, comes from the soil. And so the most important part of agricultural production is managing the soil, and more importantly, managing the life of the soil. And for some reason, conventional agriculture don't think that way. They don't think about managing that life. They think mostly from the soil, from the soil up, and not, or say from the top of the soil up, and not from top of the soil down. What we are doing with this technology, and what we who are in the area, the expertise of soil nutrition, we tend to look 90% at the biological component, because they are responsible for everything about that plant that you see when we speak of in terms of the nutrient cycle. So to continue on, I'm just showing some photos here. You see a photo here of a papaya. Now we are talking the shelf life, right? If you know, there's another component that I spoke about, other benefits of microorganisms, which is improving shelf life of your produce. And this is where I'm going at here. This is a papaya on the left-hand side, where you have rapid spoilage within a couple of weeks. The same papaya on the right-hand side, you're seeing that have been sprayed or used within organic agriculture, and where EM have been applied. You see this papaya in the same time having a far longer storability. And what you actually see there is yeast colonizing the papaya, other than bacterial issue colonizing the papaya. Here again, this is organic rice, 5 years store in 2 glass jars. One that is organically grown with EM, the other one that is chemically grown. After 5 years, looking at that rice, the shelf life still remains compared to the non-organic rice. So it shows that the microbiological factor in terms of agriculture is very, very, very important, and it can play its role in agriculture, in livestock, in poultry, in piggery, aquaculture, environment, industries, in terms of wastewater management, and in your daily life. I'm not sure how much time I have, but I wanted to present a case study to show soil renovation and production maintenance using EM technology in Belize. We actually did this work in the citrus industry, but I need to know how is my time.
You still have a little time, William. We started a little late, so we
Okay.
can go 10 more minutes or so.
Okay, let me just do the first part, and so you will get to understand what I'm saying in reference to the presentation. This is just showing you using EM. You could use it for organic waste conversion to fertilizer. Look at soil improvement, and of course yield. By the way, the prison in Belize uses EM technology and waste from all their livestock and poultry. That's all they do. And those are the type of production. Those guys are eating very good in terms of crop and animal production there. Here now, basically I'll be showing you this presentation in terms of EM use, EM technology and soil biological renovation in an infected citrus grove with HLB, no? Where we are using, remember when we started this presentation, we talk about the biological component and the carbon component. In this case, what we are applying is EM, which is the biological component, and the liquid fertilizers that we are using has 12% humic acid, along with the other nutrients, of course. And what we wanted to do here is to demonstrate the combined use of root drenching and foliar application. Remember, you saw the video there where we talk about where they talk about naturally microorganisms in the root, and naturally microorganisms, beneficial microorganisms are on the foliage. That same concept we take in terms of agriculture. So instead of waiting for it naturally, what we are doing is applying it. We are applying it in the soil within the root area, and we are applying it foliarly as well, that it is there. And what we just wanted to show here is to show you the improved soil nutrient availability within the and root growth and the fruit holding capacity of the young trees while doing this. Right? As you see here, there were two farms. We use a farm that is characterized as being very acidic, the soil. That is the silkgrass farm, farm 2, and the other farm 1, which is very calcitic. We applied per hectare, or say per acre, 20 liters of EM per acre within our trial. And of course, RX is the fertilizer with 12% humic acid that we use in root drench. While foliarly, we applied 2.5 liters of EM every 2 months for 6 months. This trial occurred for 6 months, along with other nutrients for citrus that you could see here. The part in green is what we applied in the soil. The part is orange is what we applied on top. And as you know, all of those foliar fertilizers has 12% humic acid. That basically your compost or your lombricompost, as they decompose, they form humic acids and fulvic acids and hematomelanic acids, all these good acid, no? And basically you could find them in a bottle, or you could put them in a bottle as well. So basically that's what we do. We apply these along with the microbial application in the soil and on top within the foliage. As you could see here, that application basically happened like that in terms of the root drench where we were doing. Right, that's the root drench application. how we did that application. As you see, it's not a chemical. So the reality is it's living. The amount that you're applying, those microbes eventually start multiplying within the area. And that's the big difference between doing chemical and doing biological application. The biological application, it's a living organism. They are the one who will eventually allow for decomposition of the grass, weeds, and other stuff that are there, and allow for those nutrients to go. And foliar wise, that what you see is how we were applying the foliar nutrients and EM together uh, on these plants that are considered positive with HLB. So just showing you the application there. In terms of the results on both farms, you could see here, all those stuff that says positive, it's just the analysis that came back to show that HLB, the Huang Longbing that is affecting the citrus trees in Belize commercially, they are all positive. All 9 trees in each area that we tested are positive. Before we started the trial, T0, and they are still positive at T6, 6 months after the trial. So our application was not to control HLB, our application was to allow for this plant to be able to absorb nutrients, because what this disease does is it basically blocks the phloem and doesn't allow for food to move from the root, from the soil up to the canopy of the plant. And eventually the root die and the plant die within a period, depending, like this case, we are talking a 5-year-old tree. Within a period of 2 years, those trees would die. What I'm showing here is just the analysis, right? This is the soil analysis. If you could see, T0 would be where that 0 is. At the bottom, what I'm showing is just a graphical view of those numbers that you're seeing there. It's T0 and T6, 6 months after. Everything in red is considered, the below the line is considered where no EM has been applied in that area. Above the line is considered where EM have been applied. And so what you are seeing there is you are seeing the phosphorus content becoming available in the soil after 6 months when we do the testing, how the phosphorus content in the soil is compared to the non-EM side. And in almost all of these nutrients, you will note they become more bioavailable within the soil as you apply beneficial microbes. This is the same thing that happens in regenerative agriculture 3, 4, 5 years after you start the process. What I'm showing you here, if you apply beneficial microbes, the same thing could happen from day 1. And so this is the area that I speak about, that transitional period where conventional agriculture farmers find it very hard to go to regenerative agriculture because of this time lag before naturally the microbes start doing this. If we get farmers to understand that this could occur from the beginning if you apply beneficial microbes, and then they continue the process of regenerative agriculture. So 3, 4 years down the road, they no longer need to be applying these beneficial microbes because naturally they basically stabilize within the regenerative system. They are there. And so this is basically what we are showing will be happening. And if we go, what is important here, after 6 months from when we started, the organic matter percentage was 1.8%. After 6 months, it became 2.5%. In the area where no EM was used, you notice it start reducing. So there was a 39% practically increase in soil organic matter. Why is that important? That is important because naturally microbes will start gravitating, beneficial microbes will start gravitating in that area. You already have beneficial microbes, but naturally they will start coming in that area because of the carbon source that is now beginning to increase in that area. And where does it save energy? If you are improving this organic matter content and it means the plant doesn't have to waste its energy releasing those amino acids and other stuff to allow for beneficial microbes to populate the root area. They instead take this energy and use it for growing, for fruiting, etc. Because you now have these microbes in the vicinity already. You already have carbon in the vicinity already. So this is that transitional phase that we are talking about that is needed. When we reach the complete regenerative agriculture, none of this is necessary because will be happening naturally within that environment. Now, if we look at the leaf issue, it's the same thing you are seeing. Remember, these plants are sick. They are HLB infected. The phloem are being blocked. But now that you are doing these applications, we might say, but we are applying these foliar fertilizers on top, but we are only applying these foliar fertilizers. We are applying these foliar fertilizers on the 2 area. The difference in this is we are not applying the microorganisms. And so the difference that we are seeing here is a result of the microorganism application, not necessarily of the foliar fertilizers that you're applying. Because if you look below the line where you are not applying EM, you are finding that the phosphorus, nitrogen, potassium, calcium, magnesium, all of them have reduced from what it was at the beginning, even though you're applying, which means the plant is using it. But the difference is, remember you saw in the soil, these nutrients became more bioavailable. So the plant can absorb it more from the root. It's right and natural area where the nutrients are coming than from the foliage area. And so you start seeing increases in the nutritional content within the plant, and that is important. We look at the micronutrients, the same thing happening in the soil. And remember, these plants are sick. When a plant is sick, the plant needs certain nutrients to defend itself. What are those nutrients? Zinc, copper, Zn, copper, Cu, boron, B. Those are very important and nutrient that a citrus plant need to help defend itself. Naturally, what we would do in citrus is we apply zinc, we apply copper against different diseases because they affect those microbes. But in this case, you are seeing in the soil, they become more bioavailable, and in the foliage, you will find out, within the foliage, we find out that the plant itself is absorbing them more because it needs it to defend against diseases. And so in a nutshell, that's what we are showing there, that after 6 months, you see these increases due to the biological component. But what happened to the root during that time? This is what happened to the root. This is in a calcitic soil. On the right-hand side, there is absolutely no change in root growth, while on the left-hand side, where EM is being used, there is the first month there's 13% change in fibrous root, 18% change the third month. By the 6th month, there were 22.8% change. This is the power of microorganisms in any kind of agriculture. This is certainly in organic agriculture occurs, and in conventional agriculture where we are employing these microorganisms, the same thing can occur as we are showing here. What does that translate to from an economic standpoint? It is known, it's a fact that trees that are affected with HLB in citrus will lose on average 40% of that crop. These trees, when we were doing this trial, only lost about 5% of the crop. From the time when we started this trial, we did an estimate of what was. By the time it finished, before it finished, we did an estimate. And you could have plainly see the areas where we are not applying EM compared to the areas where we are applying EM, the amount of fruit fall on the ground. The same thing we could show, and I will go through this fast, on the acid side of the soil. The same thing occurring, if you could see here with the micronutrients, and the same thing occurring in terms of the root growth area. In terms of losses, again, we had a 3.84% loss within that area. So in conclusion, basically the positive change in nutrient using biological microbes and carbon in the form of organic acids. Basically, we see increases in micro and macronutrients. Certainly, very important is the increase in soil organic matter percentage in both alkaline and acid soils. And that's what we saw in terms of root growth. And from an economic standpoint, in this area, what we saw basically where the commercial fields were, these guys were harvesting basically 71 bucks per acre in the calcitic area. In the acidic area, these trees, practically the guys were not able to harvest practically anything compared to the trial plot where we were. They were harvesting in the trial plot 112 boxes compared to 71 boxes, and on the farm where they didn't harvest anything within the trial, they harvested 52 boxes. So these are the things, these are the importance of microorganisms if we employ them correctly. Just other issues, just to show, in sugarcane, in soybean, in Brazil, in Belize, where applying EM, you have these mycelial growth occurring. You see the difference in soybean in Belize in the north, where we are applying EM compared to where we are not applying EM. The root growth in Armenia village with cabbage, for example, reducing disease, you could see the difference there. You see the difference in root growth compared to the area where no EM. This is in Barbados, our distributor in Barbados. Areas where they are growing chickpea, where Phytophthora was a problem, a soil-borne disease that you could see here. No EM compared to where we apply EM. Chickpea actually grew compared to the area where we are not applying. And in Chile, in terms of tomato fusarium problems, basically looking at this in terms of the root growth, no EM compared to where EM. Those cormy looking things are nematodes actually affecting the plant compared to areas where you are using EM and organic matter within those areas. So in a nutshell, and looking at this analysis, one of the things that occur when you are applying microbes, it creates an environment where beneficial microbes also natural beneficial microbes start coming, even beneficial nematodes start coming within the area. And that's what you are seeing there from analysis in those areas. So in a nutshell, that's my presentation. I know it's long. There's a lot of things that we can discuss and discuss always. So I am open for questions.
William, what we can do is we're going to take a little 2-minute break. We're going to do our poll. So if you want to grab a drink of water or something like that, and then we'll come back and we'll do
Hello.
William, can you hear me?
Uh-oh. Hi guys.
William, can you hear me?
Yes, I'm hearing you now.
Okay, what we're going to do is we're going to take about a 2 or 3 minute break so you can go grab a water or something to drink, and then we're going to do our poll and then come back and we'll do the questions where everybody will message in their questions to the pro-organic host, and then Jenny will ask you those questions and we can discuss them.
Great.
All right, so if you can stop sharing, I'll go ahead and pick up the PowerPoint presentation.
Okay.
You're still sharing your screen, William.
I'm
I got
still
it.
sharing my screen. Okay.
I got it, William.
Okay.
All right, Jenny, you want to start the poll?
Okay. Well, first of all, Dottie wants to know where you're located in Belmont, and is that the only outlet to buy your products?
In Belmopan, we are located at #1 Siboon Street. That's where our office is. That's just across from the store that is named 99 Supermarket. You could also find our products from most of the Rhymer's feed mill. That's where we have most of them currently.
Okay, and just for people to know, if anybody knows where the deli was, the restaurant and deli that Ian Anderson had in Belmont, William's office is
Right across from
right across the street from where that was. That was the easiest way for me to find it.
Yeah, the little red house where the guys doing barbecue in that same vicinity as well. Can't lost. You'll see the big sign.
Yes. Okay. All right. This person asked, Dr. Elaine has set up a system for soil testing for microbes as opposed to the industrial soil testing for nutrients. Do you have any plans to offer this type of soil testing?
Currently, plans are always there, but currently we don't have that. Simply in the US, labs exist. In Belize, those labs aren't here. So anyway you take it, we would have to send samples outside of the country.
Okay. How much does chlorinated water affect the EM when diluting for application?
Okay. Chlorinated water would affect EM, but as I always tell my clients, chlorinated pipe water that comes from BWSL, for example, if you use that water immediately as it comes from the plant, it's highly chlorinated. But what you have to understand is chlorine evaporates. So if you take chlorinated water and put it in a container, within 2 hours, 95 to 98% of that chlorine evaporates, right? So the chlorine used in potable water is simply to kill microbes that within the water that they bring in, that they treat and eventually release out to you. So in the pipes, it's there, but by the time, what we normally recommend with anybody, if you will use the pipe water, leave it out for an hour or two, and you should have no problem. The reality is, if you need to use it right away, it will not kill all the microbes. Probably 5% the most it will kill. So you could still use the water without a problem.
Okay. If a container was used with madre de cacao as insecticide, how do we prepare the container for subsequent EM use?
Okay. You use madre de cacao, it's mostly as an insecticide, not necessarily as a biocide. So the reality is, washing it out the simple way with soap and water, you shouldn't have a problem with it.
Okay.
But the reality is, I would still apply EM even with the concoction with madre de cacao, and you wouldn't have a problem with it.
Okay. This is from Susan. She said, we spoke the other day and you suggested I use the EM ag for 5 weeks. After that, is the soil healthy enough to continue on its own?
EM ag, okay. Soil conditions varies from place to place, and to say using it 5 times, I'm not clearly remember what her situation was, but certainly you would want to continue using the microbes. As you continue using the microbes, you get better results in time. I think I can't remember what we were discussing. Maybe she could clarify what we were discussing, why I said five weeks or 5 times.
Okay, because she also asked, she said, after hearing your presentation today, I think I need to add the Echo Hum with the application of the EM ag. How much do I add to a 5-gallon mix?
Okay. As you said that, I remember that person is in the north, right? I think she's from the north in
Yes, I'm up in
Corozal.
Corozal District.
Okay. I think I remember telling you to buy a product called Echo HX and RX. That's exactly the product that we are talking about. It's there at Eleanor Hardware.
Correct. So
That's-
how much do I put in? I know 2 liters to 18 liters, but then in that mix, how much of the Echo Home do I put in?
200 to 250 ml.
So that's like what, a half a cup?
Just about a cup. Yeah.
About a cup? Yeah, okay. All right, thank you.
All right. There's okay. Where you're located. Uh, okay, I'm not seeing any other questions other than somebody was asking if I was referring to Jethro Tull's Ian Anderson. No.
Silly.
Does anybody have any other questions about for William?
William, a simple thing here for me. I used the EM the other day on beans,
Yes, sir.
and it gave me some good results. And so now what I did, I tapped the place again. It's a small place. It's like 25 by 25. I planted about 2 pounds of beans in there, and I harvested 23 pounds of beans using EM. Now I chop it. I am ready to use EM again and get it ready for something else. What would you think? What do you think I can try on that? It's a little hill. It's a amount of soil, stones, pebbles, and but it did good, excellent. What would you recommend on that little thing here?
In terms of crops, in terms of what?
Well, I would say in terms of whatever crops that I can probably try on it. Corn, probably sweet corn. You think would do good there?
Certainly, you place bean there, so it's a good time to put on one of the gramíneas such as corn. That will go a long way because you have some nitrogen in that soil. Hopefully, most of the residual stuff you left in the area and probably harrow those back in. That will allow for the carbon that we are talking about. It will allow for other nutrients that remains within that was there with the bean. You already have the microbes there. Continue using the microbes, and as time goes by, it only gets better. That's all I could say. With this technology, the more you use it, the better it becomes. You will see that in time, to the point where you start seeing the suppression of the diseases and the reduced use if you have been using any pesticides at all. You know?
Thanks.
Okay, there's another question that asks, how far out from the tree should you spray the EM solution?
The best place is where the within the root zone, no? So it would be from the upper edge of the canopy into basically the trunk. But the reality is the fibrous root where the nutrients are absorbed from the plant occurs mostly within the first, depending on what size of tree, but within the first 20% from the outer canopy in. So you could spray within that area. Remember, it's not a chemical. So anything, once you're spraying underneath the tree or under the canopy, the microbes start moving where it finds food, which is the carbon source. Naturally, that's what happens. So within the drip line, let's put it that way.
Okay, and on the video that showed them applying the EM, the foliar spray and the root drench, the root drench looked like, unless they were just speeding it up, that they weren't really putting a lot on there.
In that case, what we were putting per tree, or say per acre, is 20 liters of EM per acre. The fact that there were, in the trial plot, there were 100 trees, So basically we divided that 20 liters divided by 100, and that's the amount of EM we are putting there. Of course, we add 20 liters plus 100 liter of water. So what we did was 120 liters divided by basically the 100, and more or less it was like 1.1 liter being applied more or less in the area of liquid, but that would come down to about 100 milliliters per tree of EM. Sorry, 200 milliliters more or less.
I don't see any other whoops. Here's one more here. Up. People are saying, great presentation. Thank you. Here's one. Is it better to apply before you plant or after the plants germinate?
Okay, that's a very good question. And as you saw with the little video, you can start using EM from the seed stage. From the time you start planting that seed in that seed tree, if that's where you start, you could start using EM. 1 part to 20 parts water, and you water that seed just as you would water as you would normally water. If it's a plant that you will be or say that you do direct seeding, it's the same thing that you would be doing. It's always good to do the application in that light. One of the things that I tell people though, if you are just beginning to use EM and you start applying EM in a very soil infested area, for example, with Phytophthora or Fusarium, etc. What I recommend to do in those areas is to apply EM at least 2 weeks before you actually bring in the crop. Because what will happen is when you bring in beneficial microbes into an area that is being dominated by pathogenic microbes, immediately you start having a fight for dominance of the environment. So when you bring that in, immediately the Phytophthora or the Fusarium, they will multiply rapidly to try to maintain dominance. But because you are bringing a large amount of EM at the same time, eventually that will be suppressed. And so you don't want that to occur when you have the problem when you are putting in your plants, because then it could have some effect on your plant, which means you have to use more EM right away. Now, it doesn't mean that you can't use EM when your plant is already done. What we would normally do is, instead of you doing that one application, we would tell you, okay, you will do that one application, but then you have to start doing more frequent application so that you could suppress that problem from occurring, because it's just a natural fight between, as you saw, there are good microbes, there are bad microbes, and good and bad depend on what crop you have there. And then there are the other microbes that go on whichever side. So as you are bringing the beneficial microbes, you will tend to have these neutral microbes start working on the side of the beneficial microbes. So that is just the thing there that we have to take into consideration. But certainly you can use it, and the best time to use it is at planting.
Couple more questions.
Certainly.
Lower Dover has a flowering avocado now. Can I put root application on it now?
You could use Root application anytime. What you have to remember is avocado is a tree, and they are constantly renovating their root system. All trees. And during flowering, certainly you will find, or fruiting, you will find that the plant start having far more micro roots, because they need certain nutrition. And so you will find that happening. And as soon as the flowering, or say as soon as harvesting go on, they start regenerating. They go into a lull stage, and then they start regenerating roots again in preparation for the next cycle of fruits. So you could apply EM anytime. You will always have the benefit of it when you're using it.
Okay. Dottie asks, is there a minimum amount to apply to plants or trees? For example, if you don't use enough, it's useless to use at all.
Okay. That's always a good question. And people always ask these questions because